Alrighty, welcome everybody. Thanks for joining tonight. And for those in Europe, thanks for joining this morning. These three seminars are being delivered by the winner and two highly commended submissions to the Die Cook Award. From this year on, the award is going to be called the Statistical Computing and Visualization Award, and it's open to students across Australia. First up, we have Harriet Mason, a PhD student in econometrics and business statistics at Monash University. She has 30 minutes, including questions, to talk about her software, ggDibbler. Please post your questions in the Q&A or the chat. Either will work, and we'll handle them as we can. Take it away, Harriet.
Can you hear me? Okay, I'll share my screen. Okay, and there's a lot happening here. Okay, so today I'm going to be presenting my software, which is ggDibbler, and it lets you add uncertainty to data visualizations. So we're going to start off with a motivating example, like why would we want this software at all? So our department had Walktober in October, where we all competed to see how many steps we could each walk every day. Me, being the data quality angel that I am, searched up the most accurate and cost-effective pedometers before we even started. I know what I found out is it turns out that pedometers are actually not very good at recording your steps at all. They're wildly inaccurate. There's lots of literature, which I spent far too much time reading, working this out. And so I thought that because I work in a statistics department, all of us would be this concerned about data quality. No, it turns out I was the only person concerned with data quality. We actually conducted a survey after Walktober to see if we could quantify the pedometer error. Like if we could work out how much error we were getting from these pedometers. And it turns out the measurement error that I had like researched about was the least of my concerns. So I asked people, is there any reason to suspect your step count might be inaccurate? One person said their pedometer app was constantly crashing. Someone else said they just converted random activities to step equivalents, whatever that means. And one person said they fabricated literally all of the data. Okay, so we have all these errors, and we also, along with the Walktober, had a visualization challenge where our department is trying to do a visualization challenge for this Walktober data, and we have all this error. We have all this error that we can discuss, but we also have all that other error that's discussed that we can try and quantify. But this visualization that I make here doesn't include any of that error. I'm just using the raw data. There isn't really a way to kind of include this like uncertainty or these errors in these plots, or at least like not an obvious way that will like always work. And this isn't even an uncommon scenario, you know, like it was weird, like it was difficult to deal with the Walktober situation, but we often have data that is unavailable. You know, we have anonymized data or we have measurement error. The true data or raw data doesn't even exist. We sometimes have data that is non-deterministic. So we have like bounded values or our values are estimated. We also have cases where our data is like purely theoretical. We have estimates based on theory, or we have latent variables or something like that. So based on all this is kind of like trying to visualize all of this stuff is kind of like too big of a problem. And this was also not what my PhD was actually supposed to be. My PhD was supposed to be a teeny tiny spatial example, just like one little part of this big uncertainty situation. So let's like simplify this problem down, this problem of like trying to visualize these random variables. This is a chloropleth map, and it has temperatures. It displays temperatures in Iowa counties. And you can see that there is this wave pattern. The low variance case has clearly a wave pattern, but the high variance case has actually been set up such that that wave pattern is no longer statistically significant. It technically shouldn't exist, but you can very clearly see that wave pattern. And that's kind of the problem that we're trying to highlight here. The idea of visualizing uncertainty, it's about transparency. It's about this idea that statistical validity should translate to perceptual ease. The higher the variance on an estimate, the harder that estimate should be to extract from the plot, and a very low variance in our estimate should translate to very easy. It should be very easy to extract that signal from the plot. So going back to our choropleth map, what we want is that low variance case, it to be really easy to pull out that sine wave. But for the high variance case, we want it to be very difficult. How do we test this property? I mean, I can look at these two plots, and say, oh, you can see it or you can't see it, and it's really difficult. But what we're trying to measure here is like a latent variable. And this is one of the other things we kind of had to assess when we were trying to work out how we should go about this, which approach we should take when trying to visualize uncertainty, was evaluating these plots and evaluating how well they incorporate the uncertainty. And to test it, we actually made a fake Ishihara colorblind test. So if anyone is familiar with a colorblind test, it's where you have to pull these numbers out of, and say the number to make sure you're not colorblind. We did this, but for maps. So you can see here on the left, we actually have this is a chloropleth map. It's not very clear that it's a chloropleth map, but it is a chloropleth map, where you have two distributions. One distribution makes up the numbers inside of the plot, and the other distribution is the background color. This is where the distance between the two plots is 0, and as we move across, the distance goes up to 4. On the y-axis, we have the variance. So as the variance increases, we should also kind of get and then this y-axis is the variance. So the variance here is 1. Variance of all the estimates of each of these individual circles is 1. Goes up to 2, 3, 4, and 5. And we can see here, we actually did a crowdsourced perceptual experiment to see how well it works. And you can see that, obviously, looking at the plot, you can see the same effect, that as your distance increases, you do get an effect. It's harder to see the 2 here than it is to see it right at this end. But what we don't get is this variance effect. All of these lines are constant as the standard deviation or the variance in each plot increases. What we really want is kind of a visibility of like a lower triangle in this kind of grid here. So the second approach we might take is, what if we just add in an extra variant? Like, what if we just add in an extra axis? What if we just add in an axis for uncertainty? And this is the solution that the bivariate map comes up with. This is the solution the bivariate map has, where we just kind of have our hue normally set to this, the hue is set to the temperature, but then the uncertainty now we're mapping to this like saturation, the standard deviation. The standard error is mapped to the saturation. You can see we have our low variance case, and then we have our high variance case. And in the high variance case, we can still see this wave, but we can see that at least the plots this time look different. I mean, that's something. And now we ask the question, does it work? We have our same grid of distance increasing and variance increasing. And we can kind of actually see the thing that we could kind of see with this plot already, which is that actually it doesn't really seem to be doing anything. These maps appear to be almost identical, again, to the chloropleth map. So what's kind of happening here is that it appears as though adding in just this extra axis, if your goal is to do this kind of noise overwhelming the signal thing, it doesn't really work. It's not really sufficient to achieve that goal. What we want is really these lines to be moving along with these classical tests, but we just don't get that. We just get constant values. Okay, so then we might say, like, why doesn't this work? It's not just another variable. Uncertainty has an interesting perceptual problem, which is that we usually don't want variables to interfere with each other, but if we're visualizing uncertainty, the opposite is true. We actually do want interference from the uncertainty axis. So then another solution we can have is just blending the colors together. This is a value suppressing uncertainty palette. And you can see that for the palette, what they do is as the uncertainty increases, they blend the colors together. Problem with this approach is that this is kind of just a factor of the scale. You can see here that this scale is, oh, they should be the same. I think I've messed this up. Oh, well, they are visualizing the same data, though. The scale is wrong because I just added it in, but the data should be the same, which is to say that this pattern has kind of disappeared. We can see we have like, oh, successful signal suppression. We can successfully see that we've hidden that wave pattern, but it's not really coming from the data itself. And one of the like benefits of visualizing data and getting to learn from our data is that we get to learn from our data. Like, it tells us what we want to know. We can see this as well when we do the test, where you can see that when we're at maximum variance, all the colors are the same. And so obviously you can't extract the values. And we can see that it does look different as the variance increases. But when we have this really big distance between the two distributions, we can still see, we still have this shrinking to zero. This shrinking to zero happens kind of independent of our estimates themselves, which we don't really want. It's not really conveying statistical validity. You know, it's just kind of conveying there's a lot of variance. So it's a similar problem to the bivariate map. Finally, if we have random variables, why don't we just, visualize them as a sample? And that's the solution that we come up with the pixel map. And the pixel map is kind of doing what we want. You can still see this wave pattern in the low variance case, but in the high variance case, it's actually really difficult to extract. And we can see that we get that lower triangle of visibility that we're looking for with the pixel maps. And we can see that the ability to see the signal in these pixel maps does translate to, it kind of translates to these classical tests that we're looking for. It follows these dashed lines. Okay, so we know which plot now we want to implement. We want to implement this pixel map or some variation of it because that's the plot that will do this kind of signal suppression solution that we want. We want to have this transparency. But coding it is actually really difficult. So if I was to imagine in my mind's eye, look into the abyss and what is the code that I want when I make this pixel map? It is basically just identical to this is my ideal VisuMap code. It's identical to GeomeSF. It's identical to the ggplot code. The only difference is that we have a random variable instead of a deterministic variable. I would like it to know exactly what I am trying to visualize and then kind of just like run with it, Do we have that? No, we don't. I do, no hate to VisuMap. I do like VisuMap. I used it for the entire first year and a half of my thesis. But I do think that it was just not what I wanted. It was not my ideal interaction with this kind of problem where I wanted to be able to just pass in this random variable and then just have it work. We have to do this bespoke data formatting function, then we have to pixelate our shapefile that makes up the geometry, then we have to build the pixel map, and then finally we have to visualize and print the pixel map. It's just a lot of steps. And it breaks up a lot of the stuff that the grammar of graphics does implicitly for us. And I kind of wanted the flexibility and the, flexibility and also the hidden detail, I guess, that comes with ggplot, but that I wasn't really getting with VisuMap. So I kind of have, okay, what we'll do is I decided I'm going to make a ggplot extension, right? I'm going to make a ggplot extension that will visualize this data, and I need input data. I need some kind of input to make it easier. A lot of this code in VisuMap is kind of dealing with the fact that you have to make all this data formatting. So the first step is to kind of fix this data formatting problem. And we kind of fix this by having just distributions. That's kind of like the hypothetical situation of uncertainty visualization, is that you have these distributions, and each cell you previously had a single value. Like for your choropleth map, it was a mean, it was a single value, but now it is theoretically a distribution. And thankfully, I did not have to do this. This was already done for me when I went to go and look it up and try and implement it. This is the package called distributional. And distributional, this is our Walktober data. we can represent them as distributions. We don't even have to have simple distributions. You can have empirical distributions, theoretical distributions. This is a truncated distribution. You can't take less than 0 steps. And so we have a normal distribution for each recording. The variance, the standard error is based on the, what do I want to say? It's based on the research that we did. So it's like coming in from the theoretical research. But then this distribution representation is done through distributional. I'm not going to go into a lot of detail on how distributional works because this isn't a talk on distributional. There are talks on distributional. I'm sure you can go find one on Mitch's YouTube channel. But for the time being, you just need to know that we are putting distributions as like individual values into these plots. And that's kind of how it's working. And that's how we want this system to respond. So we have this distributional tibble, which we could call a dibble, where each individual value is now a distribution. And we just want to swap this tibble that ggplot is used to having with this dibble. We just want to kind of swap them around. And to me, I'm reading this and I'm thinking this is a simple problem. This is like me a year and a half ago, maybe 2 years ago. I'm thinking this is straightforward, this is simple, this is easy. We're just swapping a tibble for a dibble. How hard can this be? And so I read the ggplot2 book and all its details and like how to build an extension. And it says, if your problem is simple, you don't need anything complicated. Just make sure you don't touch the group argument. You don't need your own bespoke scales. You don't need, anything more complicated, the compute group. And I am listening to the ggplot book going, thank you, ggplot book. Thank you for your advice. And trying to implement this scale problem and having a complete nightmare. I'm trying to implement this. This is a real image that I brought to one of my PhD meetings, talking to my supervisors to say, I have no idea why this isn't working. I've tried every variation. I am constantly being hit with an error. Every single time I try and make this extension following what the ggplot2 book says, I am being smacked in the face with an error. And so I go, you know what? Hadley Wickham was coming and he was going to be a distinguished guest at the department. And I said, you know what? I'll just ask, he's going to be here in the vicinity. I'll just ask him specifically. I go to Hadley, I'm trying to do something easy. And according to the ggplot2 book, it says if you're trying to do something easy, these things are all fine. Like I shouldn't have to touch this parameter. I shouldn't have to know this. I shouldn't have to do these things. Why does ggplot hate me? Why am I constantly getting these errors for something that is such a simple problem? To which he kind of said something along the lines of, bro, you are not trying to do something easy. You're trying to feed random variables into ggplot. And I took that personally. I was like, it's not easy. I'll show you easy, buddy. And you can actually see the moment that I snapped in my GitHub activity, where prior to October, I was but a humble PhD student working, every now and then, hitting the computer, hitting those GitHub commits. And something happened in October where I finally decided I was going to, one, deal with this scale problem that was driving me insane, and two, I was going to really hammer down where I just went ham. And every single day I was smashing this stuff out, and I was like, I am going to absolutely have this imagined function that I have. And that brings us to the software that I ended up making, just called ggdibbler. You might be thinking, did you end up making that hypothetical imaginary function you wanted? A little bit. Not as much as I want. ggplot actually doesn't let you make object versions of the geomes or the ggplot functions. So the closest I can get is adding this SF sample, but you can see here from this example that the code is identical. You can use this gg title, you have this legend position, which is the same. You can have the themes, you can mess with the scales, and everything is the same. The only difference is that this one has a fill mean and this one has a temperature distribution. So we have a distribution and a mean, and that's the only difference. The other difference is this times argument, which says how many times are you going to sample from that distribution. And I was like, cool, this is everything I want. So you might be thinking, so we're done. So you've achieved your goals. What a nice little package. No. because I had solved that one problem, I was like, I've already fixed this scale problem. This scale problem was 90% of my issues. I am going to make everything uncertain. The extensions, of course, are trivial. And so that's kind of what ggdibler ended up being. The first part is the data sets. Every single data set used in ggplot has a distributional equivalent in ggdibler where every single variable is a random variable. Diamonds has uncertain diamonds, MPG has uncertain MPG, empty cars, uncertain empty cars, faithful, economics, etc. Any geom, not just the spatial ones. Once I'd solved the scale problem, who's going to stop me? Hadley Wickham is not my god. We have anything we want. We can see that we've got here, we've got uncertain faithful, and then we've got the faithful, and again, it's the same thing. The code is identical. And here's a raster. You can do the exact same plot with a raster plot. Again, identical code. You can do any aesthetic. This is a case where we've got, text. We've got a text case where you can have uncertain text. This is a binomial, no, not binomial, a Bernoulli. Is it Bernoulli? Bernoulli is the 101. Bernoulli distribution where everything's either true or false, and you can see that the text itself is uncertain. And then we kind of run into a little bit of a problem when you get to like positions. And this is kind of really the ggplot book rearing its smug little head, because it tells you not to touch the group argument for a reason. And it's because of the way these positions work, where you've got your ggplot stack. And then if you kind of try and stack something where you've messed with the grouping argument, as I have done, you kind of end up with this absolute nightmare. But the ggplot book does not control me. You can make nested positions where you nest the distribution position inside of the position the ggplot is used. And so that's what ggdibler uses, so that you can still make stacked bar charts or any kind of position adjustments. And you can have any position adjustment. You can have an identity position adjustment. Doesn't have to be a dodge. In this case, we use like alpha, and that's how we create these blurry bar charts. Again, just as before, the code is identical. The only difference is you change your position. Instead of having a position stack, you have a stack identity. The first position element is for the plot itself, so the standard ggplot2 code you're looking at. And the second one is for how you manage the distribution. I also replicated, not to overkill it, all of the documentation in ggplot2. Every single piece of documentation in ggplot2 has an equivalent in ggdibler. This is the ggplot2. This is the ggplot2 documentation for a geom dot plot. This is the geom dot plot for ggdibler, and then immediately underneath, I have the ggdibble version. And this plot as well is continued underneath. It does create a bit of a problem when your documentation is twice the size, but you have to show them side by side. And you combine all this together, and that's how you get ggdibler, which is the software that I ended up submitting for this award and submitting for my PhD thesis. The idea is basically that you have uncertainty as noise, and any plot that exists in ggplot2, if you pass random variables in, has a ggdibler equivalent. The name comes from the fact that it's named after these dibbles. Dibblers. They're dibblers. They're little animals. Also, it's because ggdist is a different package that also uses distributional. It also visualizes distributional objects. And I wanted them to appear next to each other if you sort the packages alphabetically. And then the other reason is because a dibble is technically a distributional table. And then we go back to our Walktober example, and huzzah, I can visualize my uncertainty in my Walktober example. And you can see that we have all of the teams with their, not really well written, but we have all of our teams with their total step count, and then we have our average step counts per day. And it doesn't matter what type of plot we use can use ggdibler to visualize it. So conclusions, future of the software. I've got multivariate distributions. I want to implement them. Distributional lets you implement them. I want to build out the nested position system. I only have some of the positions. I don't have all of them yet. I want to fully fill that out. And then I also want to expand on the scales. The scales are can be a little bit finicky. but they are my enemy, so I haven't really been touching them. Finally, I want to acknowledge my supervisors. Die Cook, kind of ironic, is one of my supervisors, Susan Vanderplus and Sarah Goodwin. The experiment part where we did the fake colorblind tests, that was done with Rachel Rogers from UTS and Alison Kleffner. Mitch O'Hara-Wild and Cynthia Hung gave me a lot of feedback on parts of the design, which I really appreciated. My scholarship is funded by the AMO ZMA Scale Energy Scholarship and also the RTP stipend, and also the Number Hackathon is how I did the survey for the Walktober data. And so I should thank them too. Yeah, that's it.
Thanks, Harriet. I think we've got time for one question from the room, but I also would like, if you're online and have a question, please post it in the Q&A or the chat, and Harriet could answer them on the fly. But we've got a question from the room.
Yeah.
There is a question in chat. Perfect. Thanks, Bridget. Does this handle dates as scales in any way?
Good question. No. The way that the scales work is a little bit convoluted. I probably should have had a slide for it, but what it does is it nests a scale inside of the ggplot scale. So ggplot will have like scale X continuous and then like scale X discrete. And what we have is like scale X continuous distribution and then scale X discrete distribution. And so because there is a unique scale for time, like it's got like scale X time, I would have to make a separate scale, I guess. Like I'd have to make a second scale for any kind of time elements. Good question. It is on the to-do list. I think that's why I think I had on the thing where I was like, expand out the scales. I have continuous and discrete distributions, but no time yet. Yeah.
Another question in the chat. Are there any unexpected challenges or insights from turning this into an open source project or software that you encountered?
I feel like it was open source. Do you mean like open source, like relative to closed source, or like unexpected challenges in making this software?
Hey, Harriet, it was from me. Yeah, look, just kind of interested in your insights from turning the theory into something that you have to kind of manage and deal with other users who might want to manage it, and whether there's anything that you found was really nice or maybe really challenging apart from just the developmental side of things. I imagine a lot of people might feel a bit uneasy about putting their work out into the world and having other people use it.
Oh. I don't know. I think I've already kind of like broken that initial ground when I did, for my honors thesis, I did cassowary R, which like lets you calculate scagnostics. And I think that has like a lot of users. And I remember, I think Gigi Ali, the maintainers of that messaged me and they were like, oh, can we like depend on cassowary R? And I replied, I was like, please do not. I was like, please do not depend on my package. I was like, I do not want to break your package by doing something where I break my package first. And so I think that in terms of people using it, like I think I'm less stressed about I don't know, ruining people's. I shouldn't say this. This doesn't sound very good. I have no concern about ruining your software pipeline. I mean, your data analysis pipeline. But I think that on some level, like, I do think that a lot of the feedback I've gotten has been like good. Like, no one's ever said, I never get a message from someone like, I hate your software, it's terrible, take it down. The only feedback I've gotten is like, oh, here's how you could improve this. Like, Matthew Kay had actually a really good suggestion on how to implement it with extensions, like ggplot2 extensions, which I haven't implemented yet. But it is like a urgent plan because it was a genuinely good suggestion, which I could only get because the software was like out there and open and people could read it and see how I'd done it and then like say, hey, you should try doing it this other way. So I feel like it's more of a benefit than any kind of hindrance,
I like the
Alrighty, we might
fearlessness. Yeah. Thanks. Good talk, by the way. Thank you.
Excellent.
we'll leave it there, and you might continue to answer questions in the chat if they come up. Next up is Dr. Cynthia Huang to talk about her software XMAP. Cynthia is currently a postdoctoral researcher at LMU in Munich. If you want to unshare.
Okay, can everyone hear me?
Yes.
Good, great. Yeah, thank you. Very hard act to follow with Harriet, but yeah, thank you for the opportunity today to talk about my package, XMAP, also CrossMap. I think the name CrossMap was taken, which is why I ended up with XMAP. But so the agenda today is I want to tell you a bit about this package that sort of started out. I gave it a talk maybe 2 years ago now about how this package sort of started my PhD, where I had just made a mistake trying to harmonize some data, and like I don't know, we're like 4 years down the track, and I started like working on this package. So a bit about the sort of problem motivation. Often you will have like data that's collected under different survey instruments that are like meaningfully related. And this can be like labor data, so like occupation counts, which I'll show in an example later. It can be trade data where like across different countries or different jurisdictions, official statistics organizations are like measuring the same thing, but doing so slightly differently. And so here, like how to actually analyze this data together, you have roughly these steps where you collect the data, or the data was already collected, say by the ABS or like the US Labor Bureau. And they have what I called here like name or like categories, right? And then some values that are attached to those. So it could be counts, usually some sort of aggregate. And then if you want to combine them, you need to transform these different data and then merge them together. So the current workflow for this, or like when I first started working on a project that basically as an RA, like data munging, was like, okay, just write a script, right? And like now in the day of like LLMs, you could basically pass this problem to an LLM and like it would turn out something, right? So you have these bespoke scripts with this sort of if-then logic. So like if you started in the wrongness category, then like we map to this category K and you do it in like a certain way. And maybe then you check, you say like, okay, well, after I've done all this redistribution, I would check like the totals for each of these, like the sort of before and after should match up, right? This is fine in theory, but if you were me, and like I'm a very careful person, but it took me maybe a week and a half to find an edge case that I had lost because the sums did not line up and I didn't know why. And so like, yes, it works, but it's sort of hard to track and it's really hard to debug if something goes wrong. And you can see like part of the why it's hard to debug is, and even if you're trying to use somebody else's mappings, you have this like, whatever, 800 line algorithm. And like, I don't care who says that they really read these things. No one's reading these things. And so my sort of like proposed solution became like a whole framework that's based on like a graph representation and an equivalence between like graph operations and matrix operations and database operations, which I will not bore you with the details of, but I wrote up a whole paper that was like not even the software. But today, this talk is about the software, so I'm going to try very quickly to sort of introduce you to the XMAP package. So the features of the package are basically trying to, so I did the sort of like mathematical proof that if I represent the transformation as a graph, I can sort of represent that graph as a lookup table. And so I call those lookup tables cross maps, right? So this is based on the the idea of a crosswalk, right? So you have a crosswalk between like two different classifications, and I want to map data between these two different classifications. So I will talk a little bit about like what all these verbs mean, but like the basic thing was like I needed an implementation that allowed me to sort of create a cross map and to apply it to a transformation, because the cross map is basically a function and I want to apply it to the data. And the idea is like I did all this sort of like formal logic to basically design a bunch of guardrails. And so these like diagnose functions like check the transformation logic. So one like sensible thing is like the weights from like a given source node, like they all sum to one. So if I'm separating something on the previous page, if I've got Australia level like aggregate statistics and I want to separate it out by state, like the shares for each state should add up to one. Otherwise, you're like creating more data or you're losing data. You don't want to have missing values like on the links or no missing weights, because this is also a data loss risk. And you don't want to duplicate, because then you're like creating new data. When you're actually applying the transformation to actual data, you have to make sure that like the data that you have actually has all the categories in it. So there's no point in applying this like Australia transformation to like US data, right? Because these like won't match. And the basic thing here is like the function that's transforming your data should have instructions for every category in your data. No missing values. This one's a sort of interesting one, because what does it mean to distribute like a missing value across states? Or in the other direction, like if you're combining, like say you have data for like ACT and New South Wales, like how should you combine these? Lots of people end up treating NAs as zeros, but like technically, like with the uncertainty, they're not zeros. So you should make an explicit decision to transform the data into zeros before you transform it. And so this is sort of the idea behind these like rather strict guardrails. Okay, so 2 minutes for a very quick example. So here, for those of you who've worked with like any sort of like labor statistics, you have the Australian, New Zealand, I think it's like standard code of occupations or statistical classification of occupations. I now have forgotten. I actually looked this up just before, but anyway, the idea here is you have, this is also a hierarchical classification, but I here I'm just dealing at the lowest level of the classification. And you have like different occupation titles, and these map in some way to the international standard. And so you can see here, you've got like Defense Force Senior Officer, and that maps very nicely to Commissioned Armed Forces officers, right? And so this is like a one-to-one mapping. This is like translating from one language to another, like it's sort of really fine and dandy. This sort of aggregation, also very fine. Where things get difficult and where you end up with these like 800-line scripts is when you're trying to do this sort of redistribution between categories. And so how does CrossMap sort of help you do what you intended to do, right? Like you've designed your mapping and you now just want to apply it to data. So we're going to have some stylized occupation level counts. I picked these numbers because they're nice and round. But hypothetically, there was a survey run asking 2,000 individuals, and these are like the aggregated counts. Okay, so the first step is like you want to create a valid cross map. And so you just start with the lookup table between the first classification and the second classification. So here we've got like the first classification, some description of it, whatever. This is like a demo that's in the package that I just pulled off the ABS website, basically. So like naively, let's say we don't want to go through the hassle of like getting like context specific weights because they're not available or for whatever reason. And also, so this is a quick example. I basically just give these equal shares, right? You might think like that seems kind of crazy, but this is actually common practice. Like sometimes when there aren't shares available, you might split things and then re-aggregate up to a higher level and sort of like hope everything like sort of comes out in the wash. Okay, so then we have like these links, right? So you could think about this as like an unvalidated graph. and then we want to validate it. And really what we're validating is that like it satisfies all of the guardrail conditions before we use it to actually transform data. And so I created in the package like a custom like Tibble class or like a Tibble extension, which is a cross-map. So a cross-map Tibble. And it has like the number of unique keys. So it's got 6 here in this starting category classification, and it's mapping to 5 categories, right? So this is the 6, the 5, and it has basically all of these nodes and the weighting on those linkages. So what if you accidentally make like bad weights, right? So like instead of like doing this equal split thing, I'm just like, no, I want all the weights to be 1 because like, well, I'm just trying to illustrate how the errors work. But this is entirely possible that you, let's say, manually input these weights, or like for whatever reason, you've like imported some weights and they don't work. I have error messages for you, and they sort of tell you what to do. You can also diagnose the cross map, which is what this diagnose function is for, where it will sort of tell you, like, do you have duplicates? Are you missing weights? Or do you just have like nodes that have too much going, like too many, they're being here multiplied 3 times instead of being split. Okay, so then we can like apply it to the data. So stylized counts from before. And basically I pass into the apply xmap function a cross map, the values that I want to transform, and then like the starting key. So like what's the, what should I map from it? And this is sort of to identify this category here, this variable here, and then you get the count. And I added the reference to sort of show like, this is what happens when these get summed up. And okay, so then finally we have like this international standard data, and we have the hypothetical counts. So like onto analysis, like not so quick. What this whole process sort of taught me is that this like fairly standard data pre-processing step is actually creating imputed data. It's doing imputation at like a sort of like data set level, right? Like you started out with data collected under the Australian, New Zealand standard, and you like hypothetically are trying to impute the data set that would have been collected if you had asked these 2,000 individuals what their occupation was based on this list, right? Or you classified these 2,000 based on this like other occupation list. So that sort of brings me to very quickly future directions. There are a lot of directions that I wasn't expecting to sort of come out of this research, which like I haven't necessarily had a lot of time to work on because they've been pulled in so many different directions. But naturally, sort of graph visualizations, like making the graphs for this presentation and for like the work has been like a little bit of a nightmare because iGraph doesn't do what I want, and ggplot, I need a like gggraph grammar basically with like graph coordinates, and this is like a whole other problem. I have shown that you using this sort of cross-map object can extract mapping logic from an existing script. So this is something that I'm sort of working on. And then in theory, it would be nice if you could like edit these weights directly, or there's some sort of workflow or like interface to support that. Okay, so a bit over time, but thank you very much for listening. Please star the package so that I have justification to sort of keep working on this. But it's available on CRAN, and it's probably in need of more examples. So I'm working on it. But thank you.
Thanks, Cynthia. I think we'll take questions in the chat, and we'll switch over to our last speaker, Danyan Dai. And she'll be talking about her software meta extractor. Dai is a PhD student at UQ, Queensland, and is currently visiting King's College in London.
Thank you, Dai, for the introduction, and let me share my screen. So thank you everyone so much for being here. So today I'll be talking about my very first R package, Meta Extractor, and it's an R package designed for data extraction in Sysmac reviews and meta-analysis. And I know this cohort, some of you guys might not heard about Sysmac reviews and meta-analysis, but don't worry, I'll give you an example very soon. I know I'm currently in the UK at London, but I still like to acknowledge the traditional owners and their custodianship of the land on which we met. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections to the country. So, what is a systematic review? It is a structured, comprehensive method for identifying and summarizing all variable evidence on a specific research question. And systematic reviews and meta-analysis are pillars for evidence-based medicine, and it's also been known as a gold standard as well, and it's well practiced in the medical field. So here is an example of a systematic review and meta-analysis that was done part of my PhD. So what my PhD is looking into how COVID-associated acute kidney injuries impact on humans. So while researching that question, I tried to find that a lot of countries reported different acute kidney injury prevalence among COVID patients. So we went ahead and did the systematic review. And I'm just going to quickly show you guys what the result looks like. So overall, we extracted more than 300 papers. And for this is the non-ICU cohort, we can see this from this first plot, we could see that it varies significantly. The acute kidney injury prevalence among COVID patients varies significantly based on the income level and geographic locations. And the reasons behind that could be that the reporting problems and also as well as access to resource and reporting. So what a systematic review and meta-analysis trying to do is to pull all the available evidence from the existing literature and summarize it in a one cohort together to answer a specific research question. And so you might think that, oh my God, reading more than 300 papers, extracting the data is horrendous and is difficult. But very luckily for us, we have access to this paid subscription service called Covidence. And I'm also going to quickly show you guys how this is going to work. So in here, you can see that it follows the Prisma research guidance and also follows the concurrence for systematic review and meta-analysis as well. And here is one example of how the data extraction part of the systematic review is going to work. So this is loading. So essentially, this is an online service and it's similar to any paid academic service. University have a license for this, and we probably don't want to know how much it actually costs, but we also know that we're as a part of UQ, we have very lucky to have access to the service, and a lot of other universities might not be able to have access for this. And this is loading quite long, but I'm hoping that this would load it very soon. Okay, there we go. So let's have a look how the menu extraction works. So on this side, we have the manuscript. And here we have the numbers extracted. So we extracted the study period, as well as a very important part is whether how many patients were included and how many AKI patients were included. So basically, this template will be predefined, and on this side you have all the PDF version of this data of the manuscripts. So as you can see that going through this for more than 300 papers is time consuming. So from that, what we designed is an R package that's going to utilize large language models to help with this data extraction process. So essentially at the moment, the current package is designed to extract data from abstract for this at this stage. And also because abstract is widely available and you can download it in Excel spreadsheets very easily. And in that CSV file, with all the abstract you're going to extract, will be divided into both testing and training set. So in this R packet, there's in total 3 Shiny apps is designed within so that because people conducting systematic review and meta-analysis might not necessarily have any coding backgrounds, and a lot of them are clinicians. So we visualize all the process with Shiny apps just as easy as it is for anybody to have access to it. So all they needed to do is to use the built-in function to slip the abstract data into training and testing set. And among the testing set, then we'll have the first Shiny app, which is Glance Menu app. This app would ask human to identify the numbers by themselves. So it will be human tag at the first stage. And then to cross-reference with the human tagged numbers, we'll then move on to the prompt engineering app, which then you would use the results that you extracted earlier to see which prompt and which LLM models works the best for you. And then, so that testing set would be cross-checked by both human and LLM. And for the rest of the training set, you reuse the design prompt and models from the prompt engineering app. And here with batch processing. So for example, if it's 20/80 split, then the 80% of the rest of the abstract will be automatically processed with LLM with just one function. And because then this training set will then only be LLM tagged, will also require a manual validation app at the end as well. So at the end, both testing and training set would be human validated as well as LLM involved. We designed this procedure is to bring the human in the loop practice as well as following the systematic review standard data extraction stage would be cross-checked by two reviewers anyway. So you can see that at least this way, we're already going to reduce the human labor cost by significantly. So let's have a quick demonstration on how it's going to work. Because of time, we're just going to focus on the prompt engineering part. So in this script, let's reshare my screen so you guys could see the demonstration as well. Okay, so here is my R environment, and I'm going to load in my package, and then this, just by running that function here, I'll automatically bring up the Shiny app. And another thing with this design at the moment is that every LLM used are local, so there's no connection to the internet needed. So you can do this pretty much anywhere as long as you have locally installed large language models. And also there's at the moment no calling of API needed as well. So at the moment, everything's open sourced. So just for illustration, we're going to download a sample data. And from the browse part, we can just include the data here, which in the download folder, like the sample data we uploaded, and you can see this is being completed. So we're going to first see the title of the paper, abstract, and because this is a second step, we already have human labeled, which is called number of patients menu. And then we're going to move on to LLM. So the idea of this is that we're going to test, because this column is filled by humans, so by reading this abstract, I know that this is a critically ill COVID patients, total 80 of them. So I put 80 in the period stage, and this stage is designed to train my large language models. And on this panel here, we can select, say that we're going to use LLM to fill the number of patients and the score LLM column, which is displayed here. And there are a list of models. Once you have downloaded and locally installed all your LLMs, they will automatically show up here. So for example, we're going to test this model first. And because number of patients is an integer, we're going to say integer. In this abstract column, we're going to say that use information in the abstract column for this. So let's say identify number of patients. So it could be as simple as this. And then here you can also see we have a validation panel as well. So what this is going to do, if it's red, then it says LLM grabbed this number wrong. But if it's green, then it says it's correct. Or it's gray, it says no value is extracted. It's saying that using this LLM model in particular, it did not able to successfully extract the 80 patients that we're looking for. So let's try another one. Let's try another Alma 3. And we're going to use the same prompt. We think this is probably good enough. and let's just switch it to a different model. And it's running and thinking in the background for a sec. And you can see that now this is adding green. It means it's correctly filled in this column. And let's say, okay, this model seems to work and this prompt works okay too. And let's move on to the next one. And everything's also automatically updated. You can just say create the LLM variable, and then you can see that it's automatically filled in here as well. And I think, so you can go through for 10 of them, which we don't have time to do it today, but I also wanted to show what else. Because we really valued the reproducibility, because one of the things with large language model is that it might not necessarily consistently giving you the same results, even though we set the temperature to be 0. Here we have a log file, so you can see this is the one that has been done right now. In this log file, so every time we open up this app and finish this prompt engineering stage, it will give you the timestamp, the abstract that you were running, the model type you used, as well as a prompt, and the results as well. So time could be used as efficiency validations, efficiency evaluation. So you can see obviously some larger models takes longer time, and also it's a balance with result as well. So you can see with this Llama 3, it was successful for at least 2 of them. So this is for model for evaluation purpose for prompt and model selections, as well as to keep track and document every single thing that you interact with the large language models. So now let's go back to the slides. So this is overall results running through 100 randomly selected abstracts. So we can see that overall Llama gives a pretty high results accuracy for number of patients. And for the number of acute kidney injury patients, it's also relatively high. But what it failed to identify most of the time are start and end date of the studies. Obviously, a lot of them are in text format or not in the design format that we're looking for. So among the models we tried, there definitely some variables worked better than others. And here is an overall evaluation as well with overall accuracies and runtime. You can see that from this, the one that takes the longest not necessarily give you the highest accuracy. So at the end, I think when selecting prompt model as well as it really should consider both accuracy as well as runtime. So for future work, what we wanted to do would be expand the data extractions to full text for extraction to text as well. At the moment, we're limited to numbers. Of course, there's some syntax extraction we could do as well. And then also enable full text data extraction. Instead of just focusing on abstract at the moment, we're also extending this to entire full text with PDFs. And we also would like to enable the closed source LLM, so to allow users who actually pay for premium services to be able to use them as well. And I'd like to thank my collaborators, Emmy, and my support from my supervisor, JP, and UQ and SSA. So here is for installations. Because there are many Shiny apps, I also did a couple of YouTube videos as well. And also, I'm graduating this year, so hit me up looking for research fellows and lecture positions everywhere. Thank you.
Thanks, Dade. I think that concludes the evening, but to give a chance to ask questions of Dade, we'll just stay online for another 5 minutes, but feel free to drop out if you need to. Thanks everyone for joining, and thank you to the speakers. Great talks. I have a question for you, Dai, if there are none on the chat. So how sensitive is the system to your choice of variables that you want to extract from the papers?
That's a really good question. I think it's relatively sensitive in terms of the output accuracy, and that's one of the reasons why we designed the prompt engineering app for double check with the human tag one, because actually some especially with numbers, it tends to work quite well. But as long as they start involving a little bit of text, because we also enforce the type of data you're extracting, and it's all predetermined. So for example, for the dates, because we ask it to extract in the output format to be year, month, date, and once it was not necessarily provided in that format, it was quite confusing for the LLM. And in terms of text synthesis, I haven't, because we're focusing on quantitative at the moment, haven't expanded to text synthesis yet. So I'm also curious how that works as well in the future.
Other questions?
Hi, Di. It's Michael. You can't see me, but I'm here. I'm just going back to your original motivation of, systems to help non-programming experts extract this information quickly. Do you have any guidance on how someone like that should select a model, or is the idea that they just try a whole bunch of them and whatever one works best, they just roll with?
I think that's also why I had the log files also for documentations. I think for model selections, it could be very personal as well, because some people might value efficiency more than accuracy, because at the end of the day, the everything will be human checked once again anyway. So the accuracy could be fixed, but also depends on the computational power once is available, or how long they wanted to spend the time on running it as well. So personally, if you have a higher computation, higher computational powered computer, then yes, go nuts on the big models that you're capable of and hoping for a higher accuracy. But if you are limited with computational power, you might select a slightly smaller model and and then updated the accuracy later on when you're humanly double checking it. So I do think it's a trade-off, and I would leave this to the users to decide, because I think it's more personal choice that way. But at the end, you have the documentations of everything. So you could use those documentations as a justification of your model selection as well.
Alrighty, let's leave it there. Thanks, everyone.
Thank you.